So the problem states that the figure below shows a curve C with the property that for every point P on the middle curve y equals 2x squared, the areas of A and B are equal. And it states to find an equation for the line C. So what we're going to do in this summary of what we'll be doing for this problem in order to get our equation for C of x is first we're going to identify the parameters of A and B and our unknown point, and then we're going to find the area of regions A and B, and then we're going to set the areas of A and B equal to each other, and then finally we're going to solve for C of x.
In this picture, here we have y is equal to x squared, here we have y is equal to 2x squared, and here we have line C, which is what we're trying to find. In the math work that we do, we represent line C as C of x with a lowercase c. At point P, we gave it the imaginary value of x is equal to z, and we gave it the y value of y is equal to 2z squared when you plug into this equation right here, when you plug in z to this equation. It's also important to note that between point P and y is equal to x squared is a vertical line, and between point P and line C is a horizontal line. To find area of region A, here we have y is equal to 2x squared, here we have y is equal to x squared. We do vertical cross sections here because it'll be easier. If we do horizontal cross sections, we'd have to do two integrals, since they'll be using different lines at this point. So we use vertical cross sections. The top line will be y is equal to 2x squared, and the bottom line would be y is equal to x squared. So to find d of x, to which the area of the cross section is d of x times change of x, d of x will be the y top minus y bottom, so it'll be 2x squared minus x squared times change of x, and the area of the cross section will be x squared times change of x. Because we're doing vertical cross sections, and because area A is from the origin to point P, our bounds will be from 0 to z, because it starts from the origin to point P, and the x value of point P is x is equal to z. And so we put into this equation right here, so area of A will equal the integral from 0 to z of x squared times d of x. The integral of that will be 1/3 x cubed from 0 to z, and then when you expand that out and simplify it, area A will equal to 1/3 z cubed units squared.
So, to find the area of region B, the best method to use is the horizontal cross-sectional method because we'll need just one integral to calculate the area of the region. If we were to use vertical cross-section, we'll need two separate integrals. So why use that? So in horizontal cross-section, the formula to calculate it is just the length of the slab taken from the region times the width. So the length is given by xr minus x left. But note that in horizontal cross-sectional method, all parameters must be solved in terms of y. So our rightmost function we know is y equals to 2x squared. So to convert that in terms of y, we see that x is equal to the square root of y over 2. And our leftmost function is going to be the unknown function, which is just c of y. So let e of y represent the difference in the length between these two functions. So the area is just the length times the width, which is e of y times dy, also represented by x right minus x left times the change in y. So the final area of the slab in region B is square root of y over 2 minus c of y times the change in width, which is delta y. So to now find the area of the entire region, we have to take the integral from our lower bound to our upper bound. But we can see from the graph that the two graphs coincide at y equals to 0. This shows us that our lower bound is going to be y equals to 0. And our upper bound is just the y value of this point P, because this is where the equation y equals to 2c squared, the graph of it is seen to stop. So the y value of this point is just 2z squared. So our bound is going to be from 0 to 2z squared. and our total area of the region would be the integral from 0 to 2z squared of the square root of y over 2 minus the unknown function, which we can split into two pieces as seen. So also note that this integral cannot be easily determined because we don't have a famous method to calculate the integral of an unknown equation. So in the next step, we would ignore it to calculate the area. So if we ignore the unknown equation and we leave this simple one, the best method to calculate this integral is to do the u sub, because we have a linear function inside the square root. So let's assume u equals y over 2. Then we know the derivative is equal to 1/2 dy. And we know that our bounds are from 0 to 2z squared. But since in this u sub, all we're doing is solving in terms of u's, we have to convert the bounds in terms of u also. So when y equals to 0, we plug in 0, we can see that u equals to 0 also. And when y equals to 2z squared, u is seen to be equal to z squared. So if we change all this inside our area function and grind it out, we can see that grinding out, I mean, when we apply the fundamental theorem of calculus to integrate this and do some little algebra, we come to a conclusion of 4 over 3 z cubed. So the area of the entire region can be seen to be 4 over 3 z cubed minus the integral from 0 to 2z squared of c of y dy.
So now that we have the areas for region A and the area for region B, we set them equal to each other, and we're doing this to find line C, which is in the definition for the area of region B. So first thing we're going to do is we're going to get rid of the 4/3 here. We're going to subtract each side by 4/3 z cubed, and so there'll be a negative out here, but that'll cancel out with the negative in front of this integral. So we're left with z cubed is equal to the integral of line C in terms of y from the y value 0 to the y value 2z cubed, 2z squared. So just going to note real quickly that the capital C you're going to see from now on is going to be the antiderivative of the regular C, the actual line. So what we're going to do next is we're going to take the integral of c of y, and so according to the fundamental theorem of calculus, when you take the definite integral of something, you take that integral and then you plug in the bound for the variable inside, and then you subtract it. You plug in the upper bound and then you subtract it by the lower bound. So first thing we're going to do is we're going to have the antiderivative of the line, which is capital C, and we're going to plug in 2z squared minus the antiderivative of c, and we're going to plug in the second bound, which is 0. Now, just a side note really quickly, since c has it has a point at the origin, when you take a quadratic function and you take the antiderivative of that, you get a cubic function, and any quadratic that has a point at the origin, it becomes a cubic, will still have a point at the origin. So the antiderivative will still have a point at the origin. So c of 0 will just be 0. Doesn't matter if we're getting the y value or the x value. The cubic function will still have a point at the origin. So c of 0 becomes 0, and that just goes away, and we're left with z cubed is equal to c, the antiderivative of c of 2z squared. So at this point, the next step is to take the derivative of both sides, because we want the actual line c, not the antiderivative of c. And so when we do that, we use a chain rule, and the derivative of z cubed becomes 3z squared. And on the right side, we take the derivative of the antiderivative of c, which just becomes c. And then we keep the 2z squared inside, and we multiply it by the derivative of 2z squared, which is 4z. So at this point, we're going to quickly take 4z and divide each side by 4z. So that gets rid of the 4z, and we have 3/4 z left is equal to c of 2z squared. So as it is written right now as 3/4 z is equal to c of 2z squared, that's not really something we can use. So we're gonna try to rewrite these variables to something that we see that we can actually use and we can understand and write our answer in. So the first thing we're gonna do is we're gonna look at point P. Point P has the y value of 2z squared. So 2z squared is equal to y in this scenario. You can rewrite 2z squared as y. So c of 2z squared can just become c of y. The second thing we're going to do is just the same way that you write a function of x is equal to said function, f of x can just really be replaced with y. So you can write f of x is equal to mx plus b, or you can write y is equal to mx plus b. Same thing. So we're going to do the same thing in this case, and we're going to replace c of y with x. So it's just the reverse. It'll be f of y is equal to x instead of y is equal to f of x. So you can see that happening here. We go from 2z squared to y, and then the c of y just becomes x. So we're left with 3/4 z is equal to x. So now we want to get rid of the z and go. We're gonna switch that over to y. So 2z squared is equal to y. We can rewrite that as z is equal to root y over 2. So just a quick note here, since we're in the first quadrant, there will be no negative root, so we can just stick with the positive root, and we'll substitute z for root y over 2. So we're left with x is equal to 3/4 root y over 2. So now that we have the equation in terms of y, we want to rewrite it in terms of x, because that's just how we usually write equations, and that's also how the equations given in the problem are written. So we're going to change this to, in terms of x, we move the 3/4 to the other side, it becomes 4/3 x, and then we're going to square both sides, so it'll be 4/3 x squared times 2 is equal to y. At that point, we'll just distribute the squared, and we're left with y is equal to 32 divided by 9, x squared. So y can just be rewritten as c of x, and the line c is equal to 32 divided by 9x squared.
So to sum up this problem, some concepts that we needed to use in order to get our equation for C was using vertical and horizontal cross-sections to calculate the areas of A and B, and evaluating definite integrals, applying the fundamental theorem of calculus using some derivative rules, and having understanding of notations used for functions. And our final answer was c of x is equal to 32 over 9 x squared, which was our final equation for C. And one way that you could verify this is by plugging it into your calculator, and you would see that the graph fits with the others.